Center, and she's here to talk about successes and challenges of NHC forecasts in 2023.
Pointed up high. Hi. Well, thanks for that introduction. I'm Lisa Bucci. I'm a hurricane specialist at the National Hurricane Center. And so I just thought I'd give us an overview of what 2023 has been like from an operational perspective. So we've had 20 named storms in the Atlantic, 7 of which became hurricanes, 3 major hurricanes. Of those, we had 4 that had U.S. landfalls, Idalia being the major hurricane that hit the Big Bend area. Switching over to the East Pac, we've had 16 named storms, 10 hurricanes, 8 of which became major hurricanes. And we had a unique experience of Hillary making landfall or having impacts in Southern California. So that's something that was unique for that year. In the graphic, we have the number of active TCs shown in red. So you can see that at times we got up to 5 active TCs that we were writing on in both basins. And in the purple, you can see when we've had land-based watches of warning. So it was a busy season for us. And another graphic to kind of show that is the Atlantic, when we had that clustering of storms, Franklin, Jose, Gert, which never seemed to go away, Idalia, and then Tropical Depression 12. So it was a busy season. So I broke up this talk into what our successes were and gave examples and challenges. But within these successes and challenges, we have themes, and I'm just giving you examples of each. You can find many of them within this season. So I think our biggest success that we had were the prediction of our U.S. landfalling TCs. We started off with Hillary, something unique. But in terms of its genesis, we've had the pre-Hillary disturbance in our outlook over 7 days before it formed. And we raised it to the high category 5 days before formation. We saw this one coming. That gave us time to plan reconnaissance missions. This is something that's particularly challenging in the East Pacific, but we were able to get 5 missions into Hillary before it made landfall in that northern Baja California, Southern California region. Again, looking at our track and intensity forecast, we explicitly forecasted rapid intensification. And we had thankfully just gotten some guidance about the biases that track TCs in this region can have from Anna Dennis and John Cangelosi earlier that season. So we were able to apply that to this particular case, and you can see how tightly clustered we have all of our track forecasts. This also helped us message what we thought would be the biggest hazard, which was that rainfall. So on the left-hand side, you can see our 3-day rainfall forecast from WPC and then the observed totals, which led us to putting our messaging up front, our biggest impacts being the heavy rainfall associated with Hillary and the flash urban and arroyo flooding expected to bring dangerous and locally catastrophic impacts. This also helped us, we were able to use graphics to emphasize this message. Next, we had the example of Idalia. Idalia was a much tougher genesis case coming from a Central American gyre, but it entered our outlook when it was still on the Eastern Pacific side. And we were able to raise it to the high category a day and a half before genesis. Again, we threw all of our resources at this storm. We knew it was going to be a big deal. So we had the Air Force, NOAA P3s, and the G4 all collecting information in the storm as it developed. And, we had some great forecasts associated with it. We knew that this system was going to impact the Big Bend region, and we consistently highlighted that with our track forecasts. And we also knew that the system was going to rapidly intensify, and you can see that our forecasts are quite similar to what our working best track ended up being. This fed into having a storm surge peak intensity graph available and a storm surge watch issued in the Big Bend region by the August 27th at 4 p.m. And, when we start comparing that to at least our initial assessment of the storm surge, we can see that 7 to 11 matches a lot to what we saw in Steinhatchee, which is 8 to 12 feet. And as Jamie highlighted in his talk, there were no storm surge fatalities, which is a huge win coming off of 2022's Hurricane Ian. But with these successes come some pretty big challenges. And, the obvious theme is rapid intensification. It's still something that has been hounding us. And I did put in weakening because of the comment that Avichal made, and that refers to the unexpected weakening of Hurricane Lee. But I'll focus on the most obvious one, which will end up being Otis. So we had 9 storms that had rapid intensification. In purple, I put Hillary and Idalia. Both of those hit the US and they both rapidly intensified. But we had 3 in particular in the East Pacific that rapidly intensified that we didn't expect. Hurricane Lydia actually hit, north of Puerto Vallarta, but Otis was the one that caught us by surprise and with deadly consequences. From our genesis, you would have thought that this would have been a pretty well predicted storm. We had it in the genesis outlook 7 days before it actually formed. And in the high category, 6 days before it formed. We knew it was coming, but and we generally knew that it was going to affect the Acapulco region, but we did not see this rapid intensification occurring. And you can see from the blue dotted, those are our official forecasts, that we just totally missed it. This was something completely unexpected. But, it wasn't just us that missed it. If you looked at global models, you can see that they missed it too. I threw the GFS up there, but you could pick any model, any global model, and it missed it. Regional models missed it. Statistical models missed it. The guidance completely missed it. We were able to get 1 flight into this. So that isn't an overwhelming response for this storm. It was 1 Air Force mission, so we didn't even get the benefit of radar data. And it amounted to 2 fixes and 8 drop-ons and a handful of HD observations. And, these are the consequences of this. Our messaging initially was that this was going to be a rainfall event. And it didn't switch over to it being a wind event until about 12 hours beforehand. And you can see the kind of damage that occurred. But these are the downstream effects of, us looking at our guidance and missing it. Our messaging is off. And, they're thinking about 100 people are dead at this moment, at least according to the press. Switching over to the Atlantic, the challenges there include mostly our storm track forecast. It was a season of marginal systems and tough track forecasts that really, you'll hear in John's talk, it's kind of surprising that they were so tough. One of the toughest ones, and kind of the office joke, ended up being Tropical Storm Philippe. To say that there was a lot of spread in the guidance is kind of an understatement. This storm slowed down as it approached the northern Leeward and Lesser Antilles Islands. We thought maybe it would turn north. Obviously, it didn't. But at one point, we had a phone call with the islands to talk about the impacts. It looked like it was going to turn. We turned our forecast, canceled the call, and I think maybe 5 days later, we had to put the call back on and say, oh no, it actually is going to hit you. This is likely coupled with the intensity forecast. At one point, we were thinking it was going to strengthen and turn. Just kidding, it's going to weaken and go through the islands. Just kidding, it's going to strengthen and turn. And those models kept flipping back and forth, and our forecast went with it. At one point, I think one of our forecasters said it's going to be 45 knots all the way through, and all the other forecasters laughed at that person, and it turns out that was the best forecast. So, enormous amount of spread. the storm moved outside of our guidance envelope. What do you do with that? And I actually counted the number of times we mentioned uncertainty, low confidence, or a significant spread, and it was 58 times for just this storm. And that wasn't the only storm that we had trouble with, so maybe I'll go back and check some of the other discussions. So I wanted to end on a positive note, and that is that we have introduced our 7-day tropical weather outlook. So we extended it from 5 to 7 days, which means we're at least going to try to give people more advanced warning. So it's new, we extended it. That means that our guidance sometimes looks like this. And so if you're going to take on a Genesis project, it would be to help us with some of this probabilistic approach. So, you know, I happened to be on shift that day and remember looking at that and scratching my head and trying to figure out what to do here. We ended up with this graphic. So our graphic's gotten a lot busier, but hopefully we highlighted all the things that needed to be highlighted. The thing in the Gulf ended up being Tropical Storm Harold. In the Caribbean, that was Hurricane Franklin. So we were able to identify those systems, but it took everybody on the forecast floor to help me do it. So I was literally grabbing in everyone, including the director of the Hurricane Center, to say, what do you think about this? But you know, it's a success in that it gives us the opportunity to, as another tool to communicate. So that was a summary of the successes and challenges with just some of the examples. Obviously, from the season, you could have pulled other examples from each of those themes, but you know, I'll leave up the successes and challenges and take any questions from here.
And actually, Lisa, we're going to save the questions for the session at the end. So thank you very much. And our next speaker is John Cangelosi. Okay, there you are. And John's going to talk about NHC verification.
Good morning, everybody. And Lisa, that was me with that 45-knot flat line. That was half lazy, and as Eric said, in hindsight, genius, but mostly lazy. All right, so what I'm going to talk about is a bigger picture view than what Lisa showed. We want to look at the season stats as a whole from the Hurricane Center, then evaluate the models, and then really start to evaluate HAFS. That's really where our emphasis is. And I want to show you where we are in recent history. So let's start with the Hurricane Center statistics, and I want you to focus first on the orange line. That represents our intensity areas average for the whole season in the Atlantic. So preliminarily, we broke one record at 12 hours at roughly 4 knots. That's low error. No other records broken. But if you look down at the table at 120 hours, our average intensity area was only 13 knots. That's pretty low. Maybe a cash award low, Dan. I saw you here. But not record-breaking low. So, but they're near records, and I'll show you where that stands in recent history. Now, I wish I can give good news about track, but that's just not the case. The track errors were notably above what we normally put out. The average errors went up at a typical rate, or an average rate here, of about 40 to 50 nautical miles per day. And by the time we get to day 5, it was roughly 250 nautical miles, which is a big number by today's standards. Now, as Lisa just pointed out, Philippe was the biggest problem of the year from a track perspective. A lot of us wish that storm just never happened. So I thought, hey, what if it didn't happen? Let's just take it out. What if Philippe never happened? Well, the average track errors then go to that dotted blue line. That's a 20 to 25% reduction just from that one case, which is pretty notable. And where's Philippe Papin, by the way? We really picked on Philippe Papin the whole time. I was sending him texts because we put out headlines. I was saying Philippe's fate is uncertain. And I would say it applies to you as well. He's a good sport. All right, so feeding back on what Lisa was talking about, let's look at the average track errors for these individual storms. And this is just one forecast time at 72 hours. And we only picked the storms that had a pretty good sample, meaning that these statistics are relatively robust. Here is our preceding 5-year mean, which is roughly 90 nautical miles. So that's averaged between 2018 and 2022. And I know the names are a little hard to read there on the y-axis, but you can see relatively an equal distribution of forecast errors below and above the mean. As Lisa pointed out, we did really well for Lee, really well for Idalia, kind of where it counted the most for landfalling systems. But look where Philippe is. It's way out of the pack. The average error for that one storm was in the low 200 nautical mile range at 72 hours. That's a big number. So if you look closer, you might notice some patterns here. And what I'm getting at is we struggle with the weak stuff. I know in reality, there's a lot of interest when you look at case studies and do research on case studies. There's a lot of interest in looking at the big hurricanes, the ones that rapidly intensify and how that affects track. The reality is that's not our problem from a track perspective. Year after year, our problem is with the weak systems, the ones that are vertically lopsided, sheared, where the models give us inadequate guidance and are inconsistent. Take a look at the 2023 result. The systems that were initially weak are shown by the blue line. Those are the NHC track errors for the weak subset, less than 50 knots. The red line represents the storms that were stronger initially, 50 knots or higher. And you could see the big difference from our NHC track error. It's roughly 100 nautical miles by day 5. So we need help. Here's where we need help with the weak, vertically lopsided, sheared systems and their behavior from a track perspective. All right, so Lisa showed some bulk statistics, which are useful, how busy the season was. Another sort of statistic, if you like, that we look at is how exhausted are the forecasters by the time the season ends. And I can tell you, I always feel like crap in the month of December. I don't know about the fellow NHC people, but I'm just sleep deprived and tired, just don't feel great. And it seems to be correlated to this. How many forecasts did we actually issue on an annual basis? And you can see there's lots of year-to-year variability. This goes back to 1990. The mean, if you smooth through all of this, is 325. The Hurricane Center in 2023 issued 452 forecasts, so way above the mean. In fact, it's the 4th busiest from this metric since 1990. And unfortunately, we're still watching a system in the Caribbean that might put Lisa back on midnight shifts as soon as tomorrow. Sorry, Lisa. All right, let's take a look at our track error trends. Now, I'm not going to sugarcoat it. This graphic doesn't look good. And if you zoom into the right side of the graph, you could see where the 2023 track errors fit in recent history. It's a big spike up, especially at days 3 and day 5. And we need to investigate why. Obviously, Philippe was part of the problem, but even if we take Philippe out, if you just look at the blue line that ends at 250, it would only go down to 200. So it would still be pretty inflated relative to recent history. I don't have an answer. I'd love the community to get together to evaluate this. A couple of theories I think we should check out is we had a lot of systems in the subtropics and the mid-latitudes this year. Our track errors are typically correlated to latitude. That'd be one place to start. Secondly, we had a lot of weak stuff, as Lisa pointed out. Our track errors are typically correlated to intensity. So these are 2 areas certainly to investigate. The linear trends are impressive. If you go back over time, you can see they're pointed downward very nicely over the past couple of decades or so. But if you zoom in a little closer to the right-hand side of the graph, from about 2016, and I didn't draw trend lines just for that data, but the trends would be a lot flatter. We're not making a lot of gain really over the past handful of years, nothing like we were making a decade or 2 ago. So we're kind of coming up into what seems to be a brick wall. We're not getting the same returns. So I'm not exactly sure why, but this is what the data shows for now. All right, let's look at the caliber of the season and go through our standard metrics. So the first metric we look at for our track error performance is how good do we do against ourselves? And that's the black line. So the solid black line is the 2023 track errors from NHC. The dashed line is 2018 to 2022, our preceding 5-year mean. And you can see those errors were close to one another through about 60 hours. But after that, they separate with the 2023 errors being above the 5-year mean. No surprise, you can see that in all the other graphs we already showed you. What's interesting is you do not see the same pattern in the Clipper data. Notice that the Clipper errors are basically on top of its 5-year mean. And the general way we interpret that is that the season was about of average difficulty from that metric. I think there's more to the story. though. Not sure that's telling us everything we want to know. All right, let's evaluate the models for a minute. So we're in skill space. This is all against Clipper. The first thing I want to point out is look at where the models peak out, roughly at 70%. From doing this verification work for NHC over the past, I don't know, it's probably too long now, but the reality is that is a low number. Typically, we see the models peaking out closer to 80%. So we lost some skill this year against Clipper. Where does the Hurricane Center fall on this graph? Well, it's highlighted there. It's the black line. If you can see it, it's up near the top of the pack. That's where the Hurricane Center typically is on an annual basis, as skillful as the best models, which are the consensus aids. What is different in 2023 was the performance of the European. It's that blue line that I just highlighted. That was easily the best individual model and as good as or better than the consensus aids at the end of the forecast period. Now, I get what you might say. Oh, what else is new? European was good again. It's not this good normally. The European typically has 5 to 10% lower skill than the consensus aids, and we beat it just about every year. It was particularly good in 2023. And yeah, it was the best model for Philippe. So we're all interested in HAFS here, and we need to start evaluating it. So I want to show you how we do this operationally. So where did the HAFS models fall? Now I know this is clustered, and thank you to John Martinez for these graphs. HAFS B is in that purple shade. So it's up here near the top. I don't know if I have a laser pointer. That's all right, you can. It's on here? Oh, there we go. Well, apparently I'm illiterate. All right, well, it's up there near the top. HAFS B was good. HAFS A is in the light green shade, even a little bit better. These were good track models in 2023. I would say a surprising to the upside performance for those models. Notably better than the HWRF, which is in pink, and the HMON in dark green. Show me. Oh, thank you. I was pressing the wrong button. Now, what didn't do well in 2023 was the GFS. It's the dark blue line right here. Notably less skilled than the Euro, the middle of the pack, and it's never a good thing when the Canadian model outperforms you after 36 hours. But that was the case for 2023 for the GFS. That's where it was over the whole season. And I don't have a bullet here, but the NavGem was the worst performer in 2023. You could just say that just about any year. All right, so even more important than evaluating the skill of individual models to us at NHC is how does it affect the consensus? Because the consensus provides stability. What we're looking for at NHC is not just a skillful model. We want consistency so that we can make the right moves from forecast cycle to forecast cycle. And the consensus aids provide that to us. So try to follow me here. I have this labeled as the past, present, and future consensus aids. What I mean by the past, which is that black line, our baseline, is when we did not have HAFS. We only had the global models, the HWRF, and the HMON. The orange line represents the present models, where we do have HAFS, and we still have HWRF and HMON. And you can see the present version is better than the past. But what's even more promising is if we look at the future version, where eventually HWRF and HMON get retired, that gives the best result overall. I don't know how to go back. Sorry, here we go. There's the future version. So that's a big thumbs up for HAFS, something very promising. And I honestly wasn't expecting that result. But that's kind of where the good news for HAFS ends from an operational standpoint. And I'll kind of move forward and show you the results. So let's look at the intensity errors. Now, I mentioned in 2023, the Hurricane Center did a good job. Not record-breaking, but good. And if you look at the statistics for 2023, you can see they were generally flat from the 2022 levels or down for some of the longer lead times. But there's a lot of year-to-year variability. But even if you smooth through the year-to-year variability, you can see the trend lines are all pointing down. Again, really thanks to the efforts, as Frank pointed out, from this community and all of the advancements in this program that's helped produce these results. How did the intensity models fare in 2023? Well, the Hurricane Center is up top in black, so very skillful overall. In fact, we even beat the intensity consensus in the short term and in the long term, lost in some of the middle forecast periods, but beat all of the individual models in this basin, which is more traditional. Also, if you look at the skill levels, remember for track, we peaked out at about 70%. For intensity, we're peaking out around 35, 40%. That's normal. So you could still see there's room to grow here from an intensity skill perspective off of decay shifter. What was the best individual model? Best individual model was HMON in 2023. I don't know about the fellow forecasters in NHC, but every time I'm on the forecast floor, I look at the HMON, I'm like, well, that doesn't look right. And I don't really use it, but it verifies really well. So I'm not doing something right as a forecaster if that model continues to win. And that was the case in 2023. Best model from 36 to 96 and competitive at the other times. HAFS-B was pretty good though, not too far off of the HMON prediction. HWRF was notably less good, and HAFS-A was the worst for the intensity models in 2023. In fact, HAFS-A was competitive with the GFS, which is not something that you want to be proud of in this case. And again, just like we talked about before, let's look at how it affects the consensus for intensity prediction. So if you look at the past version, that's your baseline. Remember, there's no HAFS. The present version, there's HAFS and there's HWRF and HMON still. You get a little more skill. But if we get rid of HWRF and HMON, the future version has a notable degradation in skill just using HAFS in the global models. That's a red flag for us at NHC. That's a result we don't want to see, because this is our pride and joy, if you will, our intensity consensus. This is our baseline. This is what we work off of. So if we're going to degrade it, it's a big, big concern from our viewpoint at NHC. All right, let's get quickly just to the basin that you all care about, the East Pacific. So unlike the Atlantic that was way above normal, we're about 10% lower than average in terms of the number of forecasts in the East Pacific, 294 issued. I'm just going to get right to the chase here for the most important statistics from our view. How did HAFS affect the track consensus in the East Pacific? In general, I'd call this all in the noise. Whether you have the past version, the present version that includes HAFS, HWRF, and HMON, or the future version without HWRF and HMON, you generally get a similar result. We'll call those small differences. How about the intensity guidance in the East Pac? So this is a very different result than the Atlantic. First, you can see skill levels are a little higher. They're up just a little north of 40%. They peak out. The Hurricane Center prediction is actually better than the consensus here, but there's an individual model that did really well. And that individual model was HAFS-A. The same model that was the worst in the Atlantic, that was barely competitive with the GFS, was the best model in the East Pacific. Honestly, I don't know how to figure these things out. Even further, the HMON that was the best in the Atlantic was the worst in the Pacific, down at the bottom of the pack. And we'll call the HWRF and the HAFS-B. HAFS-B was actually not bad, so that was a little more consistent in both basins. And then lastly, GFS was really not competitive at all. And again, how does this affect the intensity consensus in the East Pacific? Well, the good news is the HAFS is helping a little bit, because if you look at the present version or the future version, it's a little bit better than the past version. So I guess I would summarize, if I would look at the HAFS, I would give it a thumbs up for track in the Atlantic, but a big thumbs down for intensity in the Atlantic, kind of a thumbs sideways overall for its performance in the East Pacific. So I'll just wrap up here. In summary, in the Atlantic, it was a tough year for track. And we're going to have to further study this, and we will at NHC. But we'd love to collaborate with this community to figure out what's going on. The Euro was particularly good this year. Not just normally good, really good in 2023. The HMON's still best model for intensity. And guess what? It has been for the past couple of years in the Atlantic. It's sort of the motto of doing less is sometimes more. The HAFS made the track consensus better and the intensity consensus worse. And for the East Pac, I didn't have time to show you all statistics, but this kind of summarizes the deal. It was a good year for track. We were generally near record-breaking track performance for the East Pac, not so good for intensity. Euro was best model in the East Pacific, but it was more competitive there. HAFS-A, as I just showed you, was best for intensity. And overall, the HAFS kind of made little impact overall in the East Pacific. So Jessica, I'll pass it back to you. Thank you.
Thank you very much, John. Yeah, we'll save all the questions for the end. So next up is Dave Zielinski from NHC, who will be talking about the NHC technology and science activities.
This. Gotcha. All right. Hello, everyone. Good morning. This is going to be a little different. It's still going to be an overview of NHC operations, but from a very different perspective now, looking at the technology and science branch, which is one of the three operational branches at NHC. So I'm going to talk about that at the beginning. I've done this the last couple years, but I think every year you get new people in the community. Someone may have missed something. So I'm going to talk a little bit about our operational environment. Think of it as the 2-minute whirlwind tour of NHC technology. And in the end, also talk about some of the STI HFIP supported work from the last year. So this is the staff in TSB. Pablo is in the back. He can raise his hand. We have a branch chief. Last year, this time, we didn't have one. So Pablo is the new leader of TSB. He'll be here today. I think he'll be here tomorrow. So if you see him, there's his face. It's not hard to find him in a crowd. So say hi, introduce yourself. He's been around in the community for a while, but new, I think, more to some of the researchers on like the EMC side. So NHC mission critical software. Kind of summarizing it into 4 parts. You have AWIPS 2, which is kind of our primary way of looking at model data, looking at satellite data, looking at observations, and so on. You have the ATCF, which of course we share with JTWC, we share with CPHC. That's how we create our forecast products. It's also our interface with WCOS2. When we run HAFS, it's from inputs from the ATCF. Then you have the web. Of course, we use that to view things that we don't have in NHC systems, and NAWIPS. Now, if you remember this slide, I actually grabbed this exactly, copied and pasted from last year's presentation. It looked a little different, and you'll notice that NAWIPS is the number 2 thing on that whole list. In the past year, we've basically crossed out, and certainly by the 2024 hurricane season, we'll have crossed out all operational use of NAWIPS at NHC. It's a big deal because if you've been coming to these meetings for a while, you might remember like my predecessor's predecessor in my role talking about the NAWIPS to AWIPS 2 transition at NHC. And it's actually happening for real. It's amazing. So we are going to be using AWIPS exclusively for warning collaboration. We'll be using AWIPS for all of our graphics. The surface map will be done in AWIPS. So it's a big deal for NHC. It's a major project, a significant amount of our time. I think we did the math, and over half of our time in STI employees is spent right now on this project. But it's well worth it in the long run to kind of consolidate our technology. So I told you I promised you a 2-minute whirlwind tour of NHC technology. Here we go. Input sources comes from all over the place. We get data from NCO, we get data from the SBN, which is available to everyone. I'm not going to read all of this to you because this presentation is going to get posted to the HFIP website afterwards. And my hope is, as you are developing new technologies, new methods, new whatever it is, you're going to come back to this and you're going to say, what does NHC have? So I can use that too and develop something that is useful. So think of this as a reference. The key thing is that everything is going to come into NHC through official channels, and everything's also going to leave NHC through official channels. That limits us to some degree. You know, we can't just create anything we want and send it out to the world. It has to go out, for instance, through our AWIP system if you want to edit a text product. But again, hopefully you can use this as a useful reference. Coding languages that we're using at NHC. This hasn't really changed. We're trying to stabilize. So for languages, we're primarily using Bash, Python, and Fortran for new things. You might be thinking to yourself, why Fortran? Well, you still can't really beat it if you need to do a lot of number crunching really quickly. I'm not going to stand up here and tell you that these are by far the best languages for every single application, but I am going to tell you that NHC is made up of meteorologists, not computer engineers. We don't have the experience to learn 15 different languages for 15 different optimal ways to do some form of math. But we do have the ability to learn a couple of them. So we can focus on these It's going to make us more efficient going forward because at least we'll be all kind of talking literally the same language. Platforms, the one I want you to focus on is AWIPS 2. You saw we crossed off NAWIPS. The idea in the long run is we're going to essentially cross off everything but AWIPS. So if you're thinking about a display for a forecaster, for instance, you should be thinking about doing it inside of AWIPS because it's basically AWIPS or the road at this point going forward. Some highlights from 2023. I've been hitting the NAWIPS to AWIPS thing over and over on basically every slide, but it's a big deal for us. It may not matter to anyone in this room other than the NHC forecasters, but it's a big deal to us. And I think it's important for the researchers to realize that when we say, hey, I'm sorry, I didn't have time to get to that. This is why. This is, I think in the very first talk, we talked a little bit about Ken's 10, the NWS's 10 biggest areas of focus. This is one of them. And this only affects a couple offices in the whole weather service. So that's how big of a deal it is. Other big ones, PSurge 3.0. I believe the very next talk is going to talk about that one. The operational use of the wind hazard recommender, we're going to talk about that shortly as well, but we're kind of revolutionizing how we do warning collaboration with the local offices. A big one for HFIP is the HICA. So we've been talking about HICA for, gosh, about a decade now. It ran in full operations for the first time in 2023. 100% managed by NCO, run in real time on the supercomputer. It's a long road, but it's there. It's in full supported operations now. And of course, HAFS as well. Challenges. I mentioned we have a branch chief now, but we didn't for a big chunk of the last fiscal year. I actually looked back, and in the last 5 years, TSB has had about 75% turnover in our positions, our federal positions. That's high. And it's not necessarily because it's such a terrible place to be. Some of it's because we've had good people that have moved on to bigger and better things. But that is another reason why we're trying to kind of standardize things. The more standard things can be, the more similar we can be from application to application, the easier it is for us to continue moving forward despite turnover and other things. We also eat a lot of our time in IT security related things, whether it's operating system migrations, migrating to CAC login. I don't know how many people are federal employees, but a year ago, no one at NHC used their CAC to log into anything operational. And today, they only use their CAC to log into everything operational, just about. Unfortunately, we don't have an army of sysadmins at NHC. That means our meteorologist, STI staff have to eat these to make it work for us. So between the desk flip, the NAWIPS AWIPS 2 transition, and this, you can really see where our time kind of starts to go. All right, so getting into things that are more in line with what everyone here I think is interested in. Again, not going to go over all these in detail, but here were 3 of the big projects we had in terms of STI milestones for the last year. A big one. So storm surge, polygon-based watches, warnings, and hazard services. Bit of a mouthful. The important thing here is we're trying to improve how our warnings are communicated with the public. So rather than, whoops, can I go back? There we go. Rather than say warning an entire large zone connected to a coast, the idea is warn the area that is directly potentially affected by storm surge, similar to, say, the inundation graphic that we use. The big news here is that in 2024, we're going to be testing this on NHC's live AWIP system. Not transmitting to the public yet, but taking a step forward to improve our hazard communication for storm surge. All right, HAFS at NHC. So John actually touched on this in terms of evaluation. I want to show you, this is actually something that we did about a year ago as we were evaluating whether or not HAFS was going to be operational, and then what was going to happen with HFIP and HMON. NHC forecasters don't just pick one model and go with it. Now, apparently, based on the 2023 Atlantic season, we should have picked the ECMWF for track at longer ranges and gone with that. But generally, we are forecasting through the lens of the consensus, because we know no one model is going to be best from run to run, or from storm to storm, or from year to year. So looking at the impact of halves inside of the consensus and inside of the smart consensus, HICA, for instance, we were able to show 5 to 10% improvements by having all 4 models rather than turning off HWRF and HMON. So again, John mentioned red flags. This is something that it concerns forecasters. We're at a point right now where we've actually improved the forecast guidance that NHC forecasters are using the most by having all 4 models. And we see a lot of indications that if we turn the 2 others off at this point, you're going to start losing some of the gains that we are seeing. We're working on getting HAFS and AWIPs. Again, if you want a forecaster to see it, it's got to be an AWIPs. And we're using the cloud. The idea is we don't have to take down NHC's operational system to do tests. We have the ability to do it in the cloud now in a development sense. All right, operational forecast guidance and updates. This is, SHIPS, LGEM. There's a whole host of updates. Because of the WCOS updating schedule, we hadn't had a chance to do updates in a couple of years. So this was kind of a relatively big year in terms of updates. The whole list is here. Again, in the interest of time, I can't read them all, but you can always go back and take a look. The wind speed probability also got some updates, and there was a improvement in how it handled land in particular. Now, I think at the end of the week, we're going to talk about wind speed probabilities 2.0, which is a far more radical change. But for this year, we saw some small incremental improvements. Other work supported by STI money. This is something we don't really have time to get truly into the implications of it, but some of you may be familiar with the concept of using AI for forecasts. And there's a few modeling groups around the world really that are trying to do this now. The idea is you make an empirical forecast based on reanalysis fields. So you train an AI model based on reanalysis, and you say, all right, here's the current state, what's going to happen 7 days from now. And it takes a lot of computing effort to train the model, but then what you get out of it will run, in this case at Sierra, in about 40 seconds on a single workstation. And the result is something that produces track forecasts up to 5 days out that are as good as the GFS and one workstation in 40 seconds. There's a lot of implications here. There's no physics, right? This is almost like climatology on steroids in a way, but it's pretty cool. Maybe it's something that will revolutionize how we do ensembles. I don't know. Wind hazard recommender. So the baseline software that we use for collaborating with local offices on warnings was available at NHC this whole season. We actually used it operationally during Hurricane Hillary. So that's the first time where we were using AWIPs to collaborate with the offices. In 2024, we're retiring Nmap entirely, and that'll leave us with just the AWIPs tool. Another thing is looking at forecast variability. So trying to get a better feel, not just for which models are most accurate or which forecasts are most accurate, but how do those forecasts change from cycle to cycle? You can imagine NHC forecasts, we can't afford to, our forecast can't go back and forth because no one will trust us, right? You need to build trust with the forecast or with the public. And likewise, NHC forecasters lose faith in models if it says, I'm going to be, forecast 100 knots and then 50 knots and then 100 knots. You're not going to use that. So this is coming up with ways to objectively determine what that consistency looks like, get a better feel for both models and again, like the official forecast. All right, last slide. Looking at 2024, things that are upcoming for the next year. We still have some big OS software migrations. I mentioned Red Hat 8 earlier in the talk. We're working on shifting our focus to development in the cloud. Again, that gives us a way to visualize things in AWIPs before they go onto our operational system. Wind speed probability 2.0. Pablo and Wallace have a talk on that on Friday. I highly encourage you to take a look because it's going to really revolutionize how we look at wind speed probabilities. Continuing to improve our technical infrastructure, and then there's some longer term goals. Ultimately, the goal is we get down to a single platform. Everything goes in and out of AWIPS 2, so the forecasters are just looking at everything there. And that's all I have.
Thank you very much, Dave. We'll take questions at the end. And next up is Laura Alaka from the Hurricane Center, who's going to talk about operational storm surge modeling.
Hey everyone, my name is Laura Alaka. I'm here representing the Storm Surge Unit at the National Hurricane Center. Andy Penny is actually online and he's going to be co-presenting with me. Andy, are you there? Can you just...
Yeah.
Awesome, we hear you.
Great.
So today I'm going to be talking about the operational storm surge modeling updates that we've had. I'm going to give a brief overview of the season as well. So just to get into it, this slide is giving you the probabilistic storm surge model introduction. We call it P-Surge. This is our main source of guidance for issuing all storm surge watches and warnings. P-Surge is based on an ensemble of the slosh model. We use slosh because it's computationally efficient and we can complete hundreds of simulations in our 1 hour time window in order to provide our operational forecasts in a timely manner. This image is from Hurricane Ian showing the P-Surge ensemble. You can see at the center of the P-Surge ensemble is the official forecast track. And the P-Surge ensemble is, it's perturbed using a statistical method. And you can see that the cross-track perturbations in this case encompass the best track of Ian. And so that demonstrates that our statistical method was working here. Aside from perturbing track, we also perturb the forward speed to account for changes in tidal cycles. We also do the intensity. We have 3 members, and we perturb the size of the storm using the RMW to dictate that. First, I wanted to talk about a season recap. We had Hurricane Idalia make landfall in the Florida Big Bend region. This image shows the maximum water levels from the event. Here we have the blue symbols representing the sensors that were greater than 3 feet above mean high or high water. We use mean high or high water as a proxy for above normally dry ground. And so the blue represents greater than 3 feet. The pink represents greater than 6 feet. You can see that we don't have that many sensors in this area, but our highest sensor was recorded a water level of 8 feet above mean high or high water in Steinhatchee, close to the landfall location. And I just wanted to demonstrate here, this is the timeline or the hydrograph from this water level sensor. It's actually a USGS sensor that's located about 2 miles up the Steinhatchee River. And you can see that overlaid on this is the timeline of the watches and warnings that were issued in a timely manner prior to the onset of tropical storm force winds. And this sensor ultimately reached 8 feet right around the time of landfall. And interestingly, the sensor only records every 15 minutes, so it could have missed the max water level between. There was also significant damages in Horseshoe Beach, which was just south of Steinhatchee. This was an extremely exposed coastline, and they likely received significant wave damages on top of the storm surge inundation, although we have no water level sensors in this area. So we basically have to go off of field crews going into the area, aerial imagery to assess the damages, as well as model hindcasts. I did want to get into what the P-Surge guidance looked like for Hurricane Idalia. So on the left is the P-Surge guidance 36 hours prior to landfall. And you can see there's significant storm surge risk all along the Florida Big Bend. This is the 10% exceedance, or that near worst case scenario. And you can see there's significant risk in Tampa Bay specifically. There's a lot of track spread when we're 36 hours prior to landfall. But as we move closer in time, 12 hours prior, the risk in Tampa Bay significantly drops off. While we do have, a decrease in the track uncertainty, we know as forecasters that the risk is still there for Tampa Bay, and we're left wondering what's going on here. Well, we know that one of the weaknesses of the P-Search model is the wind field, the outer wind field. And so this image shows that Idalia had a really large 34-knot wind field on that east side. And the best track as it was offshore shows that the 34-knot wind radii were out to 150 nautical miles from the center. The blue line shows the slosh radial wind profile at the same time. And you can see that the slosh wind profile just wasn't able to capture that large wind field, and it didn't capture that storm surge risk in Tampa Bay. So again, this is the hydrograph of the guidance, as well as the observation from a NOS tide station in Tampa Bay. The black line among these is the observation, which reached about 4.5 feet above mean high or high water. And you can see that 12 hours prior to landfall, our guidance actually dropped below the observed water level. But as NHC forecasters, we know this weakness of the model, and it's one of our active areas of work is to improve this the radial wind profile and be able to capture the wind away from the center from that RMW. So we've made a lot of improvements to P-Surge over the last 5 years. We've had a lot of successes starting from version 2.7 in 2018 to version 2.9 in 2021. We did a lot of work to improve the input and the forecast of the RMW in the P-Search model. And so we're able to control the size of the wind field via that RMW parameter. And this led to a lot of improvements in the verification, significant improvements in the threat score. And then in this year, we made a very significant upgrade in version 3.0. We kind of switched gears and focused on adding non-uniform manning and bottom slip coefficients, as well as coupling slosh with a wave model to provide services for Puerto Rico and the US Virgin Islands. And this required a lot of technical updates that was, a really big feat for our group. So this is just an example of what the manning and bottom slip coefficient differences are going to look like for the previous version of P-Surge on the top and the current version of P-Surge on the bottom. And at a coastal station like the one circled here, you're really not going to see very much difference in the probabilities. We're looking here at the probability of exceeding 6 feet. So the probabilities really are unchanged at these coastal locations. But moving to more inland locations, you see that we have the forecast is reduced in these inland locations. The probabilities are going to be lower. And one of the great things that we were able to implement here is that we reduced over forecasting, but we didn't compromise the skill. And then this last update was providing services for Puerto Rico and the US Virgin Islands. We have not actually issued this yet this season, thankfully, but this was a huge service upgrade for this area. We've now coupled slosh with a wave model, and this is an example of what the potential storm surge flooding map would look like for Hurricane Maria. If we had this service available back in 2017. And through verification, we've been able to show that for this location in southeast Puerto Rico, the guidance is able to give us important warning decision information 48 to 60 hours prior to the onset of hazardous conditions, which is in our watch warning timeframe. So this was the 3.0 upgrade, and Andy is going to take over now online to talk about the future work, where we go from here.
Yeah, thanks, Laura. If you could advance the slide. Okay. I'm going to be talking about some of the things we're working on to try to improve P-Surge. Some of these are ideas, and some of these are things that we're actively working on. And one area of focus is to try to improve and understand the wind field that's used to drive the atmospheric forcing for the surge model. And as Laura showed for Hurricane Idalia earlier this year, the wind field was much too small, and this caused the probabilities in and around the Tampa area to be too low. And this was, an issue as Idalia got closer to landfall. But that's not always the case. Is if you look at Hurricane Ian from last year, if you look at the wind field on the figure on the left here, you can see that for Ian, the wind field was too large. And this was an issue, and it caused some of the probabilities in a few of the areas we forecast for to be too high. And so we had to make some adjustments for that. And so one of the things we're hoping to do is to use the WTCM model or test it, is to use that in slosh instead of the parametric wind profile from slosh. And the WTCM is a gridded wind field that's surface-based, and it's actually based on NHC forecast parameters. So if you look at a radial wind profile here, the figure on the right, for Ian, this is from the southwest quadrant, and the blue line is from slosh. And you can see that the wind field in slosh was just way too large for Ian. One of the other limitations of the slosh parametric wind profile is that it really can't handle any asymmetries in the wind field other than those that are due to storm motion. So this is an issue for weaker systems that occur in the early or late season. And we often have to turn to other guidance like PETS for these types of storms. We'd also like to explore whether we could use the extratropical storm surge model, ETSS, to define the solution away from the storm. So sometimes you might have a frontal boundary or something ahead of the storm, and we're currently not able to account for that in slosh. Okay, next slide, please. So another project that we're working on is to try to extend P-Surge out into the Pacific, notably for the Hawaiian Islands, Guam, and American Samoa. And you can advance the slide. And so slosh grids do exist for these regions, but we're not currently running P-Surge in real time. And so this is a project that Ben Trabing from the Storm Surge Unit and Arthur Taylor from MDL are working on. Okay, you can advance. So the first area that we're hoping to run P-Surge in is Hawaii, and this animation here shows a single track slosh run from Hurricane Iniki from 1992. And Iniki was really the last major hurricane to make landfall in Hawaii. And so, one of the challenges we face is just coming up with a good set of cases to verify against. But this is something we're just starting to get into. Okay, next slide. So just to kind of provide a quick summary of what we've done so far and what remains to be done for extending P-Surge into the Pacific. Ben has worked on developing a technique to blend forecasts from the Eastern Pacific with the Central Pacific, just because we have so few cases in the Central Pacific. And it's really important we have a large sample to compute the track, intensity, and RMW error distributions. Those error distributions are used to generate the P-Surge ensemble. So that work has pretty much been done. Some of the remaining challenges, a lot of the slosh basins for these regions are going to need to be reconfigured just so that they can run within an hour. We only have an hour operationally on WCOS to run P-Surge. We also need to conduct stability tests for these slosh basins using the parametric wave model. and running with tides, and then develop a ConOps plan for running P-surge in the Pacific, which includes data flow and product dissemination. The next slide. So just to provide a summary for kind of what we've done and where we want to go. Again, P-surge was upgraded to version 3.0, and that included the manning in bottom slip coefficients, which really helped reduce the inland extent of the storm surge inundation without really compromising the verification metrics that we use. We also added service for Puerto Rico and the U.S. Virgin Islands, and those slosh grids are coupled to a simplified wave model, which is very important in that area. And then, yeah, so looking down the road for future work, we'd like to try to improve the wind model that's used in slosh, and we're investigating whether we could maybe use the WTCM for that. And then we're also working to build out P-surge in the Pacific. And that's all we have. Thanks.
All right, thank you, Andy and Laura. Next up is Jim Nelson. Jim's going to be joining us remotely. He is at the Weather Prediction Center, and he is going to be talking about WPC rainfall forecasting for tropical cyclones.
All right, thank you. Good afternoon, good morning, everyone. So yes, as was introduced, I'm Jim Nelson. I work at the Weather Prediction Center in Development and Training Branch Chief. Happy to join you here today. Been working with the Hurricane Center as well as AOML over the years in this position. So it's thank you for inviting me today. All right, on to the next slide, please. So just something that we've been doing the last few years is just basically trying to keep track of the wettest U.S. tropical cyclones since 2005. So we can see that Ian joined us in 2022. We didn't have any in 2023 that joined the top 10. But still, we didn't update for Idalia yet because the season's not over with. And just trying to keep that in perspective as to where we're at and when the latest ones have happened. And you can see that a lot of the latest events have been pretty large in the last 5 to 6 years. Okay, on the next slide. So we just kind of categorize what we have as far as the top 10 most prolific tropical rainfall days since 2005. These are based on the area of 10 inches or more of 24-hour rainfall. So you can see that it's just the area basically. You can see that Harvey is on there a few times, and Ian jumped in the third place with its track a couple last year. Okay, on to the next slide. So I'm just going to start with an overview of what WPC does in the process. So, WPC overall does a lot of different forecasts for the CONUS, winter, QPF, temperature, threats in days 3 to 7. We also do Alaska for days 4 to 7, and we do some stuff for Hawaii as far as heavy rainfall is concerned in CONUS. As far as the tropical cyclone rainfall statements, we work with NHC and CPHC on those statements. That covers the Atlantic and Pacific basins as well as the Caribbean. International Desk also works with the Hurricane Center on tropical statements, maybe not named storms, but prior to it actually being within the warning category. And whether it's going to be landfall on U.S. territory, that's when WPC takes over. But the International Desk does the rest of the Caribbean and South American areas and Central American areas. And that's a kind of a combination with our responsibility with USAID within the State Department to help for IDSS and be a messenger for the impacts due to that rainfall. On to the next slide. So here's how we kind of produce, our QPF from WPC perspective is, we do days 1 to 7 as far as QPF is concerned. We try to zoom in on tropical rainfall from days 3 and 4 on in. We have a probabilistic QPF page that we're looking at days 1 through 3 to try to get an idea of what's the probability of, say, 2 inches happening, 4 inches happening, those kind of things. What we've recently done in the last few years is we're expanding on other products. So the Extreme Preset Monitor is something that compares QPF relative to the recurrence interval. We're looking to expand that out to day 7 in the near future. So that's going to take into account not only WPC QPF, but also model QPF, and maybe some probabilistic aspects of that as well. We extended the ERO, the excessive rainfall outlook, to 5 days now. So we actually are still, and we're looking to go to day 7 eventually in the next couple of years. And then one of our, more detailed products, trying to hit the first 6 to 12 hours of where the threat is from heavy rainfall is the mesoscale precipitation discussion. So this is something that during, an event like a landfalling tropical storm or hurricane, we're hitting it with the ERO, we're hitting it with the probabilistic products. We, you have the detailed tropical rainfall graphics. And then, just to highlight certain areas where there's banding or a persistent, boundary that's happening, training effect aspects. So we want to hit the, where those things are happening in the next 6 to 12 hours. So you have the general overall aspect of it, but you want to make sure that you're really hitting the local areas. All right, moving on to the next slide. So where our information fits, we work with entities within the Weather Service, Hurricane Center, forecast offices, RFCs, Water Center on the key messages during an event. Obviously, the rainfall forecast is making its way onto the hurricanes.gov site, as well as the ERO, flash flood potential forecast. Eventually, we're going to have something for the international area on there, and we're working with. I'm working with Jamie on how that's going to influence and how that's going to be presented on the webpage for the international areas. Okay, moving on. Next slide. So international support. Just want to talk a little bit more about that. So the desk itself is tasked with training meteorologists from Mexico, Central and Northern South America, as well as the island nations of the Caribbean. And that's in response to the tropical area or the tropical desk itself. There's a South America desk that we do all the countries for South America as well. During the hurricane season, we issue QPF for IDSS, and that's over Mexico, Central and North South America, as well as the islands in the Caribbean. We provide the basis for the rainfall hazards and rainfall and hazard statements. We just did one yesterday. So for the area that you have 70% chance of something forming. So we have a nice graphic out for that. We started that yesterday. So looks pretty bad for Haiti at this point and Jamaica. So we'll be keeping an eye on that, and we'll keep going forward with that. Some of our primary users of the product are the Hurricane Center, WPC, USAID, the National Hydrological and Meteorological Services of the RA3 and RA4. So secondary is some of the DoD sites. We're getting more and more interaction with DoD. So South Command is one of the biggest ones for us. And then we have Navy, Air Force, and Army aspects. So those have increased over time, and just as part of that USAID process, we're making sure that all entities are heard and related to and met as far as requests. So not only is it making it to Hurricane Center, WPC, USAID, but we're trying to get into we're working with the military services. Okay, next slide. So part of that collaborative forecast process, that we work with is, we get the MBM, we look at QPF, we kind of look at that, come up with our first guess, our preliminary WPC aspect. We work with the offices, we work with Hurricane Center, work with the international desk, and we get the final QPF and we send that, and that becomes one of those graphics. And then we later on look at, how well we did. So, what's the idea of us getting, what's our errors, what are we looking at? Okay, next slide. So one of the biggest things that help us communicate the threat or the risk is the excessive rainfall outlook. So what does it do? It's a situation awareness and planning tool that gets your head in the game. It's not a specific forecast for flash flooding. It accounts for uncertainty in placement, timing of intense rainfall, and hopefully summarizes the days 1 through 3. But and that's what we're trying to put on the page right now, and we're moving that to days 1 through 5. So we'll see how that goes as far as the messaging and the combined ERO that we've done over the years for days 1 through 3. How do we work that for days 1 through 5? And when does it become? Do we slide that scale? Does it go 2 to 4? Does it do 3 to 5? So those are things that we're contemplating going forward as far as the sliding scale of that combined ERO that we've done over the years. Next slide, please. And again, just to highlight, there's obviously the mesoscale precipitation discussion, and we want to make sure that we highlight any areas that are blowing up based on the conditions, and that is particularly true with landfalling hurricanes and tropical storms as to where the banding, where the intensity is, so that we can highlight areas that may need more assistance or more mitigation and more awareness of this situation going on. Okay, next slide. So, those are the big challenges, right? We have all tropical storms, cyclones produce rain. So what, right? So how many are localized hotspots? And that's where the mesoscale, discussion comes into play. So it's, how do you motivate people to move? So few with widespread rain, but there's catastrophic rain as well. So people want us to get these things right. So how do we minimize these errors? And this is where I'm going to talk about some of the products going forward and what some of the challenges are as far as that's concerned. So moving on to the next slide. So the predictability challenges: small, less organized storms can still produce localized extreme rainfall maximum. So as Harvey had something, but where were the hardest parts to talk about? So, and you can see the difference between Imelda and Harvey here. But
Jim, just 3 minutes.
Okay, all right, move on then. Next slide. So some of the other predictability challenges: banding. Let's move on. Obviously, probabilistic is the way to try to get an idea of how those areas are being concentrated, how the areas are being looked at, where the probability of having those higher criteria met, where the higher threat may be, based on the probabilistic data set. So moving on, next slide. Just wanted to hit on these really quick. So what we have right now is we're working on a probabilistic precipitation portal, which we hope is prototype right now, available inside the Weather Service. We're working on an urban rain rate dashboard, which basically says, okay, what kind of areas have infrastructure that are vulnerable, and what areas are, and what time, and what does it take to be vulnerable? So that's one thing. Burn scar, basically, again, that's based on where there's fire areas. We have an object tracking page, which is based off the HREF, the high res ensemble forecast system run by the Weather Service. So we're trying to track objects itself and give an idea of where there could be heading, like the heavy precipitation, like 1-inch rainfall objects, 2-inch rainfall objects. Try to get an idea of where those things are heading and what tracks are looking like and what the cloud of uncertainty of that track is. So we're working on those. So that'd be a good product to look and watch. We have a clusters web page which gives you different scenarios on where the things may go, based on like some analysis of the EOFs to know which way the storm may go and what kind of different scenarios are out there. We have started our MetWatch verification, so our MPD verification, and there's a paper that'll be coming out in the next few months, hopefully. And then we're thinking about adding additional probabilities within our ERO. Next slide. So what we've been doing the last few years is displacement error calculations. I think you've seen this slide before. So it's basically based on QPF, and we're looking at the object of precipitation and how far it's displaced from the object of reality. So moving on. So what we did is the last few years, we added 23 here. So what's our displacement error of the 2-inch rainfall contour? from the prior year, so 12 hours into the forecast, we're 53 miles as far as the error. The 2-inch error is concerned. That's 2 miles less than the year, the 2016, 2022 displacement. 60 hours is 98, and 108 hours is 151 miles, so 19 miles less. Moving on. So this was something we did last year with the comparison of the HAFS, and we can see, since that's something that we're looking at and what we want in our forecast process, we can see the HAFS displacement error is actually less than WPCs and less than the MBMs. So it's something of use to forecasters. And the next slide, we looked at Idalia. Here's the impacts. We'll keep moving on. I'll just show them the last slide. Next slide. Here's their combined ERO. There's Idalia. And then here's Idalia's, and we can see a very good forecast from, this is using WPC as well. And I'll just say, moving on, keep going. And the last slide, one more. So this year, I think, oh, go to that one. Yeah, so it was useful within forecast process. And I think that might have helped with some of our displacement error this year, just basically looking at this one storm itself. But we felt, the use of HAFS this year in the forecast process was very good. And as Dave mentioned earlier about getting HAFS into the AWIPS platform, it's going to be a big bonus for us going forward as well. So that's something we're looking to do as well, too. And that's it. Sorry, went over a minute.
Thank you very much, Jim, and please hang on for the end of the session where we'll have our Q&A. So our last speaker for this session is Levi Cowan from JTWC, who is going to talk about the utility and behavior of HAFS A in JTWC operations.
Hi, it's great to be here. I'd like to focus this year's presentation on HAFS for obvious reasons. Went operational in late June. JTWC started using the model in July. And evaluating, how it behaves in our basins, it's a little different. Doesn't have vortex DA, some of the fancier things. Certainly no benefit of aircraft recon data that we have in the Atlantic and East Pac. This is the sample set that we have. No Southern Hemisphere season has kicked off just yet, so everything was in the Northern Hemisphere, mostly West Pac. This was an El Nino year, lots of long track super typhoons. They're in dark pink, so we have a lot of intensity, high intensity and low intensity cases in the data set. We even had a super typhoon in the Arabian Sea, so that was neat and unique. But in general, about 13 storms, 11 of which were in the West Pac. And I want to talk to you about a couple case studies, really, about how HAFS kind of jumped out to me as a forecaster who actually sat a couple of watches for some of these storms. This is Typhoon 6 Whiskey. Can you tell I'm an employee of the DoD now? It crossed into the East China Sea from the southeast. Yellow part of the track there is typhoon intensity. And then it does this slow down and sharp right hook within the East China Sea. So as you can imagine, there was some upwelling, pretty shallow water there once you cross the Ryukyu Islands. And so we had a rapid weakening event. So I'm going to cut across the grain here a little bit and talk about RW. And this was obviously ocean driven, but what was so interesting was how HAFS performed in this particular case relative to HWRF. This is some of the ocean products available from the EMC HAFS archive page, and I want to thank you guys for running that. It's immensely valuable to have these graphics available posthumously. It's really, really helpful. This is the SST on the left and the OHC on the right, showing the total collapse of the heat content under the storm. And as you can imagine, this turned off the heat fluxes at inner radii. So this is the initialization of the HAFS run on August 2nd, showing the inner core still intact, and then the 21-hour forecast showing the complete collapse. And so what this typically does, of course, is it leads to a broadening of the vortex. And so in HAFS, here's the initialization 10-meter wind field from the same run, showing an RMW of about 23 nautical miles. And then within 54 hours, or a couple of days, we have a distinct broadening of the RMW all the way out to about 90 nautical miles as the inner core basically gets cut out like a cookie cutter. And of course, HWRF is going to capture this process as well, just not quite as accurately as HAFS. For whatever reason, it shows the weakening, but not the same degree of broadening. You can see the tight RMW there of about 16, broadening to 57, but not quite as much as the HAFS model. And when we look at observations, this was an ASCAT-B pass from around 0Z on the 5th of August, around the verifying time of those forecasts I just showed you. And the observed RMW was a lot closer to the HAFS forecast than it was to HWRF at about 80 to 90 nautical miles. And so HAFS verified pretty well here. And it's like, okay, you know, big deal. The vortex broadened out, it's weakening over cooling water. Does this matter a lot? Well, it did in terms of the ensuing intensity forecast. This is the comparison of the 5-day wind field forecast from HWRF on the left, HAFS on the right. And what's unique here is that the storm started moving over warmer water again just prior to moving into southern Japan, which you might be able to make out on the HAFS graphic, the Japanese coastline in the northwest quadrant there. And so there was a reconsolidation period after it moved out of the cold oceanic wake, where you can start to see tightening of the vortex again, contraction of the RMW, and a little bit of re-intensification. In the case of HWRF, there was actually a fair bit of re-intensification back to typhoon strength, 70 to 75 knots before interacting with the Japanese landmass. But HAFS showed about 20 knots fewer of weakening at only about 55 to 60 knots. And the reason for this was the broader vortex during oceanic upwelling. And so this rapid weakening phase and the ensuing structural evolution, better represented in HAFS, meant that there was less contraction possible within the short time window before hitting Japan. And the verifying intensity here was indeed about 50 knots, so on the weaker side of these dynamical forecasts. And so this was one example that jumped out to me immediately of how HAFS handled this upwelling case and the structural broadening and then recontraction in a better way than HWRF did, just for this one case. The second case that really jumped out here was Super Typhoon 9 Whiskey, Saola. This was one that did kind of a looping motion east of Luzon and strengthened to a super typhoon between Luzon and Taiwan, and then ended up moving into southern China while weakening, approaching the coastline. But this storm was chaotic in terms of inner core evolution. It had multiple secondary eye wall formation events, eye wall replacement cycles. The first one occurred during that track loop at the first green X, the rightmost X, east of Luzon on August 28th, and it had a second ERC south of Taiwan. This first ERC is what catapulted it into its super typhoon phase at the beginning. And this is a sample, again, from the EMC webpage archive of the simulated radar shots for a bunch of model runs, forecasts 4 to 5 days lead time out, valid on August 28th or 29th, showing the secondary eye wall formation that was occurring on a lot of these model runs over and over and over again. And I will say, you know, HAFS does create more secondary eye walls than HWRF does. I think most people who watch the model fields realize this. So there are occasionally, you know, probability of detection is inflated a little bit with, you know, some false alarms thrown in there, but HAFS was remarkably consistent in this case at predicting at long lead times this inner core evolution, the formation of a secondary wind max, and then subsequent intensification to super typhoon intensities. And it even caught the secondary ERC after this one. In a lot of these runs, it would do one ERC complete and then eventually form another secondary eye wall and perform another cycle. This is very interesting because HWRF rarely does this, at least from my anecdotal observation. It'll do one ERC, a big broad eye, and eye wall will result, and then it will stay a large donut forever and kind of get stuck in that configuration a lot, at least in the Westpac Basin. HAFS has less of that problem, much more inner core diversity, and you can see some of the, you know, complex structures being modeled here and rather consistently from run to run to run, which was really nice to see. This ended up verifying pretty nicely. This was the AMSR 2 89 gigahertz microwave pass we got at 18Z on August 28th. So within plus or minus 12 hours of all of the model runs I just showed you, that's what it looked like. It was pretty close. The SIMS ring score Havmaler is on the left there, so you can see how the first ERC, the secondary eye wall, started forming on the 26th, and then the ERC on the 28th, and then the second ERC down at the bottom of that Havmaler began a couple of days later. So HAFS verified pretty well on this particular case. Now, of course, there are some challenges and quirks, shall we say. This was the biggest head scratcher of the year by a mile. This was Super typhoon 15 Whiskey moved up northwest of the Marianas and Guam and recurved into the mid-latitudes. Very, very strong typhoon. For whatever reason, during the vast majority of the typhoon's lifetime, the TC vitals were resulting in an initialization that was far deeper than any other model, including HWRF's own initialization. 30 to 50 hectopascals lower in this particular case. The panel on the left was HWRF at 905 millibars at peak intensity, and HAFS A was 853. So putting the 850 isosurface right into the ground. Not good. And you can see that, you know, the maximum intensity actually was pretty similar. They were not that different, about 155 knots, but the reason the pressure was so low is because the wind field was so broad. So broad, in fact, that, you know, I went and I plotted it. In the top left is the pressure trace. So you can see how not just that one model cycle, but days of model cycles, the pressure was very, very low relative to CAR-Q, the black line, which is our TC vitals input, the real-time best track. You can see HWRF in blue was very close to that for the pressure trace. It was also pretty close for maximum wind, which HAFS was okay for. But on the bottom two panels, that's the 50 and 64 knot wind radii. So that's the inner core size. And again, HWRF in blue, very close or close-ish with the TC vitals, but HAFS off in its own land with a massive inner core, especially evident with the 64 knot wind radius. Not really sure why, no idea, but it definitely stood out. I would have to do deeper digging to see if this actually occurred in more than just this storm, but this one, it was such a big difference, we couldn't help but notice. So in summary here, I think one of the coolest things I've noticed, you know, HAFS A demonstrates a lot of increased variability and diversity in inner core structure evolution. And that doesn't mean that it's necessarily getting everything right, but I have noticed some successes, like the ones I showed you with the ERCs, with the oceanic induced weakening and broadening. And some of this structural diversity, I think, is really pointing in the right direction, because like I said, anecdotally, HWRF would get stuck in a certain configuration for long periods of time. I don't sense that problem with HAFS. And so from that perspective, it's really useful for a forecaster to go in and look at the two-dimensional, three-dimensional fields, see how the inner core is being modeled and what's influencing it, and be able to make adjustments to your forecast based on that knowledge. Like I said, unlike HWRF, we get even multiple eyewall replacement cycles, which is really interesting. And sometimes it gets the timing right, even with the second one that follows on. As I mentioned, vortex initialization is occasionally dramatically different from HWRF in unrealistic ways. But, you know, despite that, HAFS A in green on this plot here was one of our best individual intensity models for this year so far, based on preliminary best track data. It was competitive with COAMP's TC, which is actually the better model at some lead times, but not all. You'll notice that we kind of struggled this year in general. If you look at the y-axis, the day 5 intensity error for the consensus is 24 knots. I think NHC was down at 13. So, I mean, goodness, we had it's rough out there. We really need recon. But JT in red, we were below 20 knots at all lead times, beating all models, including the consensus. So we're not out of a job just yet. That's all I have. I want to thank this group for their work and development of the HAFS A model. I think we're finding it useful, and I can't wait to evaluate it further and see new updates. Thank you.
All right, thank you everybody for holding your questions to the end. We now have 15 minutes Q&A for all the speakers, and given that list of presentations, I'd be shocked if there are not questions for our speakers. Frank.
So why are we still verifying intensity when structure is so important at landfall? Structure is driving the surge, structure is driving the wind damage. John, why didn't we see any structure verification? John Cangelosi. Oh, there you are, hiding.
Yeah, that's actually underway. I'll take this. That's okay. That's actually underway. Brad Reinhardt, who's not here, is taking the lead on that. So he's looking at as much structure verification as we can. So really what we have is like 34, 50 knots, like a lot what like Levi showed.
10 years ago, we thought it wasn't, at landfall, we thought it was pretty good. the most important metric. Not doing it.
Right. We're behind. Well taken. We're going to do it.
No, the community has to do it. We need to start thinking about it this way. I think we're missing the boat. I mean, intensity, we're in the uncertainty time right now. 10 knots is what we can estimate is our uncertainty. Why are we wasting our time with that? Let's get on to structure at landfall. I think that's more important.
And part of the problem is we probably don't have a verifying structured database, I'm guessing, right?
That there's probably work that should be done there. I think we can do it.
You want to cut it this one, Kate, or?
Reanalysis.
So yeah, we do have work that's getting underway on attempting to address this, and there's several different aspects that are looking at. One of them is you'll hear more from Pablo on, or I think we'll also be presenting it on WSP 2.0. But part of the issues there is establishing a ground truth to actually validate against, and that's some work that we're taking on with the storm surge unit to look at the surface wind analyses and seeing if we can take some of the efforts that have been done so far and create an analysis of record.
If Frank just, I think it's same thing, same as reanalysis. If we don't have reanalysis, how can we verify or validate our improvement? Right now, we almost reach the minimum, the uncertainty of the best track. We still focus on these three numbers. We're going to have very limited measurement to measure our model improvement.
I think Deb had a question. Deb, did you have one? Pablo.
Go ahead.
My question is, in light of what John presented with H4, H1, I know those two are scheduled to be phased out next month. So is that going to be talked about?
I'm guessing that's probably a sidebar. It might be too soon to ask someone to go on record for that one unless they care to.
Just from my perspective, it's a decision that's outside and above HFIP proper.
Right.
That would have to come from the NCEP director's office through consultation with lots of folks. So I don't think it's a decision they're willing to make at this exact moment.
Some of those verification metrics are being seen for the first time. Probably need to give people a hot minute to like digest it all and figure out what to do. Yeah, Dev.
Yeah, so I was again going back to the issue of rainfall and how we can use the rainfall verification, especially from hurricanes. And when you're looking at this national scale swaths, they all look great. But when the application, particularly from where we have highest populations like cities, I think it will be helpful if we can identify some test beds. And so when you're talking about how do you verify that, so I'm thinking like Houston and some other regions around, Miami maybe, and where this could be done in a consistent mode with a dedicated projects. And I wanted to see if there's some activity going on like that, or what could be a way that we could continue doing this at a much local scale for urban applications.
I'm guessing Jim, if you're online, you'd be the best. No.
Can you repeat that? Sorry.
I think in quick summary, if we were to test the performance about the cyclone rainfall in urban regions, rather than just a large national statistics, is there any program out there which could be tagged along, or are there any concepts or test beds that could be built on for evaluating the performance of cyclone rainfall for hydrological applications, particularly in cities?
I think that's a great question, and I would take that up with probably the Water Center and the Cooperative Institute there to think about how we could tackle that problem. I know we're trying to do the urban rainfall rate dashboard, which will probably focus us on on the verification of these urban corridors. So that's, something that we're working towards currently. So we'll have a better viewpoint of those as we develop that project, and we'll be able to define those urban corridors a little bit better so that we can have the verification on that. And I wouldn't put it past ourselves to go retrospectively and look at what we have as far as our database is concerned, and being able to create those kind of metrics.
All right, Chris.
Yeah, Chris Lancy, Hurricane Center. One thing that John showed that really struck me was the improvement of HAFS models over and above the parent GFS model. In the past, HWRF and GFDL before it could never consistently improve upon the parent model. How did y'all do that? I mean, what was the data assimilation or the model structure? How did you get that? That's very impressive.
So I'm actually going to talk about this later in my talk today, but it turns out that the reconnaissance data had a huge impact in a lot of HAFS cycles, especially for weaker systems. And I can't speak to its impact in, I guess it's been evaluated in GFS, and there's going to be another talk on that, but in HAFS, for Philippe and Tammy, the weaker cycles, Franklin, all those weaker cycles, like it was improving the track forecast, 20% or more. And I have some examples from Philippe that are just breathtaking. That looks like it has a pretty good forecast when you have the recon. When you take it out, it looks like GFS. So I think that's part of it. I don't know, that's fully the answer. I don't know if I don't want to steal EMC's thunder. If you have any other comments about that.
Yeah, I was looking at you several times when they showed the results that you were always, since 2012, you were mentioning about this, that HAFS has been behind GFS, and now is the time that we have. One of the reasons that I'm starting to see, of course, JSON inner core data is important. Also, the resolutions from the GFDL modeling system that we started with 54, 27, and something like that, we have come all the way to 6 and 2 now, basically, which means from 54 to 6. And what we see, we ran some YAN cases without any data assimilation, just running the GFS ensembles. GFS ensembles didn't get the tracks on 26th, right? But the moment you just apply the higher resolution and initialize with GFS, we were able to start getting much better tracks, which shows the point that resolution, getting the tracks right, you need to have a critical resolution beyond which you will start doing better. That's one. And the boundary conditions, the way GFS FE3 does this in regional model, it's a little bit much better than the previous model like H1.
Yeah, another point I want to add is that before HWRF and GFS use different dynamic costs, and right now HAFS uses the same dynamic cost as GFS with a higher resolution. I guess that's
back to the storms we saw this year. They were interesting. We had a lot of weak cycles, a whole lot of weak cycles in the MDR, sheared storms, and typically on an average season, if you look at the correlation between track and intensity errors, they're not too well correlated. They're, around correlation is R squared around 0.1. It's pretty low. I suspect that this year that correlation was very high. That if you go and look at some of these storms like Philippe, the cycles that recurved were on the right. They were strong, right? And the ones that didn't recurve were on the left. And this year was that dial was turned all the way up, much more so than usual. We'll see a handful of cycles like that in a given year. And that takes actually me to a thought John brought up about HMON. Why in the world HMON did so good this year? Well, HMON, I think this season played like straight into HMON's hand. HMON has a weak bias typically. HWRF is the opposite, right? It's excitable, right? And I think this year the model to be was the weak model, right? And so if you were the strong model, you're going to do, pull a GFS and go, way off to the right. So I think this is kind of the year to year, we see so much variability in the storms that we get. And, if you just look at one season, it can skew things. But this year was just, that was the cards that we were dealt.
I've got a question, or I guess just a question for John. If you remember offhand, you might not have it with you. So in terms of like the mean absolute error and stuff on the HAFS, we were looking at this in the Atlantic. Do you remember offhand if there's any sign in the bias in those errors?
Going to actually pass it to the person behind you, Brian. John Martinez. Did you know offhand? No. Yeah, sorry, Brian.
He's the smartest guy in the room. No comment.
Definitely. Yeah. When I'm confused, I pass it to that John. So sorry about that.
Mark. Yeah. Just to get going back to Frank's original question, and structure is kind of related to what you talked about. There are, and I think Kate said this a little bit too, that there's databases of R34, 50, and 64. I mean, you've been best tracking those since 2004, I think. And I think recently, maybe 2021, you started best tracking RMW. So I think that the data is there to do the verification, and I think that's a good next step. Maybe it's kind of the argument we started with HFIP. Why bother verifying intensity when it's only good to 10 knots? But I think James Franklin put in a comment. You can tell the difference between Otis and landfall and Otis 2 days before. So you can tell the tails, and you can tell the difference with the structure between a Charlie from 2004 and an Ian. One is just much bigger. So the data is there, I think, to look at at least the tails of the distribution. And then one final thought for off NHC basins where there's next to no recon is that the new synthetic aperture radar data gives you pretty nice profiles. And I think it needs to be verified a little bit more, but you can get RMW estimates like you never have before in the or when you don't have aircraft data. And that's a whole nother source I think you could use to evaluate wind structure. So the data is there to do it.
Frank, you want to respond to Mark's question first?
Thank you, Ben. James is right. You can tell the difference between a 200 knot gust and a 100 knot gust. But what about the timing? What about the storm surge? What about all these things that are dependent on structure that matter to people as well? I mean, when we did the PDT-5 and the hurricane landfall, we recognized that there were two different things going on. Landfall, yeah, maybe intensity is important, but it's really important to know the structure for all the impacts. So if you go to the impacts and not just verification, I think structure makes a lot of sense. I'm not saying stop doing intensity. I'm just saying, why are we locked in on this and not looking at the other parts? Because if we're going to go to Jamie's comment about vulnerability and things like that, it's a very local problem. And these things are, you got to map structure onto those things. That's all I'm saying.
Ben, did you want to ask your question? Then we have a question online that I need to get to.
Okay. First of all, I totally agree for the storm structure comparison. I also agree with Shijin. At some point, we probably need like an in-the-core analysis of the storm. And in that case, you will have a better chance to verify your model development. I also have a comment for Chris' question for why we are having a better track right now, especially coming out from HAFS. I think we mentioned data simulation, high resolution, dynamics. I think another very important aspect is physics. I think actually for HAFS, right now, our physics is optimized for hurricane. We're basically ahead of the GFS version 16. For example, HFIP right now is using 1% microphysics. It's the one going to be in GFS version 17. You probably notice HFIP did a great job for Philip, actually. So that's another comment.
John Nath online, would you like to ask your question or comment?
Yeah, I have,
I have sort of a comment or I got a couple comments. One, it seems our observations are letting us down. And when HFIP started, there was an observational component, and that's kind of been downplayed, and it's a modeling project. But I'm wondering at this point, do we want as a community to advocate for things that provide high resolution surface winds, both over land and over water, to do the validation of these models, which are now at extremely high resolution and seem to be getting the structures right? My second question is, so we saw that the European Center had the best track forecast this year, and almost everything that we look at in track and intensity forecasting is based on sort of the GFS parent. And I'm wondering that, is that putting all our eggs in one basket? And should models that are not driven solely by the GFS be part of the effort and to improve sort of the consensus of multi-models? And yeah, so those are my two questions. And I've been advocating that we should be doing structure verification for 10 years. And yes, the data was never perfect. But now it's better, and we've made no progress. And so I think it behooves the community to just start doing it with caveats and presenting it, because the only way the structure forecasts are going to improve if you know how bad they are. Okay, thanks.
As expected, a passionate topic. I'm going to synthesize this really quick so we can go to lunch and try to bring everybody's home. 10 or 15 years ago, we made track our moonshot, and John showed that we've made substantial progress and may be approaching the limits of predictability. Then we made intensity our moonshot, and while we're making progress, there's still room to improve. I think there's a consensus emerging that we might need to make structure, because the point of this meeting is our next generation strategic plan. Structure our moonshot, set metrics and goals accordingly so we can start getting there. Sarah's going to start some work on this courtesy of the IIJA/Bill project. Kate's probably not ready to talk about it yet, but we are going to start putting money where our mouth is on this one. And I will let that be your fodder for our lunch discussion. You want to tell us the lunch logistics?
Yeah, okay. John, I'm sorry we couldn't get to the rest of your question. I just do want to add real quickly that I know it seems like HFIP has shifted completely away from observations. That is not the point, the intent. Priorities shift as the whims of leadership and money also shift. And HAFS was a very strong priority of the Weather Act to get it out quickly. And that's something we've definitely done, but our observations are still on the plate.
Yeah, no worries. Yeah, it just.
That said, I do have to just ignore lunch break. I'm sorry to cut you off, but.
Oh, okay. Yeah.
All right, so we will start back up promptly at 2:15. We're pretty tight on time the whole week, so that's why I'm kind of being a little bit of a time cop here. For those of you in the room, the lunch is out in the main atrium area. It should be on the left-hand side as you walk out there, and it should be just a self-serve buffet style type thing. And please be back around 2:10 so that we have a few minutes to get settled. Thank you.